second speaker is Luke Bornn. Luke Bornn is the VP of Strategy and Analytics for the Sacramento Kings. Previously, he was the head of analytics for AS Roma, and he had tenured track professorships at Harvard and Simon Fraser University. His talk today is going to be about using player tracking data to organize possessions of offensive structure. Take it away, Luke.
So the talk today is work with Andy Miller. He really deserves all the credit here. This work is led by him. I'm just fortunate enough to be a PhD supervisor. So this is work done last year, presented at Sloan. In fact, for those of you who've been to Sloan will recognize the theme of the slide. We'll look at it. So this project basically started off with something that, this idea that's sort of been lingering for a while, and thinking, can we actually go into the database of NBA data, player tracking data, or box score data, or whatever it might be, and can we pull out possessions and label them by their offensive structure? If you think about what currently exists right now, there are companies like Stats and Second Spectrum that are tagging plays. So they'll tag things like screens, and they'll tag things like pick and rolls. And the way that's done is typically by hand labeling a whole bunch of plays and then using sort of supervised machine learning techniques. What I thought was, can we do something in a totally unsupervised way and identify what's going on in possessions? The idea that you could then query similar offensive sets, so you could say, okay, find me two sets possessions that look very similar in terms of what was happening on the court, and really sort of automatic tagging of sort of complex actions without hand labeling. Really, the aim here is to sort of allow for answer a whole bunch of new questions. These are the questions that really got us thinking. Questions that we've been posing for a while. How do the Rockets create their corner threes? What is the success rate of the Warriors weave play? When do the Spurs run their hammer set? These are all things that are interesting basketball questions, sports questions, but really rely on you knowing something or being able to say, okay, let's actually isolate when did the Warriors run their weave? Can we actually label which of the Warriors sets were a weave? Can we label which of the Spurs sets were a hammer set? Okay, so let's watch a quick possession here. This is what's called the hammer set from the San Antonio Spurs, and what you see here is Ginobili's going to give and go and then drive to the basket. And at the same time, the key part that's happening here is that Devin Green's man will be pinned down right there so that he can get to the corner. All right, I'll show you another play here. So again, Spurs again. This time it's Tim Duncan with a much better screen. You're going to see it right there. And so both of these plays have the same action. They have it's a give and go, cut to the basket. Actually, that's not a give and go. It's cut to the basket. The wing is cutting to the corner. At the same time, there's a weak side screen, weak side pin down screen. Okay, so we have this idea that you can see two possessions and you can see that they look similar. So we thought, okay, how do we actually go about labeling these possessions? How do we go about sort of taking, sort of saying automatically that those two plays are hammer sets without hand labeling them? So we're actually going to use some ideas from text analysis. Here's a bunch of documents. And the top four documents are all about politics. It's Trump pushes GOP healthcare, Jeff Sessions, Trump playing golf with McElroy, Kaepernick protests. And these bottom four are about sports. So the middle two are about golf and football, respectively, and then Golden State Warriors, etc. So there are really good methods for taking a corpus of documents and labeling them and saying, hey, these four are about this topic, these four are about this topic. In this case, you have, okay, top four politics, bottom four are sports, but the ones in the middle actually share some of those topics. So there are good tools for doing this, if you, like latent ratio allocation and its many variants, lots and lots of different types of topic models. So what we want to do is try and use some of this idea, instead of thinking about a document, thinking about a play or a possession. So really, this is the framework that we're in. Instead of having a bunch of documents, we have a bunch of plays, right? And we're thinking, okay, we have a whole bunch of plays, a game sort of cut up into offensive actions. How do we actually label them? How do we do this? How do we figure out which ones are similar, which ones are different? So what we'd like to do, if we wanted to turn a play into a document, we can just label it, right? we could say this hammer set, this first hammer set, is a cut to the left wing, as Jonas sort of cuts to the left wing, and drives from the left wing to the basket. At the same time, you have a weak side cut to the corner and a pin down screen. So you could say what's happening, right? And we could write it down, and we could actually, using the sort of writing down the actions that happen, we could actually build a topic model based on that by thinking of that as our document. The problem is we don't want to hand label 100,000 possessions. So what we're going to do instead is use tracking data. So this player tracking data has been around for a while. This is sport view data coming from stats. This data gives you the locations on the court of all 10 players 25 times per second. You also get the ball. And so really what we're trying to do then is to take the spatial temporal data, this player tracking data, and turn it into a document. How do we represent a play as a document using this data? So the way we're going to do this is really by first thinking about individual action, and then after we think about individual actions, we think about how those individuals interact to make a team. All right, so here's how we thought about turning an individual player's movements into something that's usable by a topic model. The first thing we did is we took that player's movement and we plotted his speed over time, and we basically sliced up the trajectory at moments of low speed. Okay? So here you see it's a trajectory path for Harrison Barnes. You see he starts from kind of up the elbow, out of the three-point line, cuts to the left corner, etc. And what we've done is we've taken that and we've essentially sliced up his movement into chunks of sort of contiguous chunks. And so what you get is for all 5 players on the court, you get a sequence of chunks. So you're basically taking all their movement, and every player we've sort of sliced up whenever they stop on the court, whenever their speed dropped below some threshold. So the next thing is we have every play, we have all 5 players, and we have this sort of sliced up, their actions sliced up into little segments. So essentially what you can think of is that every play we have all these little segments. Now what we want to do is we want to label these segments. So we have roughly, after we slice up a whole season, we have roughly 4.5 million of these little segments. And what we want to do is we want to cluster them and find segments that are similar. So segments maybe that are baseline cuts or different types of movement. So what we're actually going to do is use a parametric mixture model. But instead of a typical mixture model where you might use like a Gaussian as your parametric model for the individual components, here we're actually using Bezier curves. So it's a normal, it's a Gaussian mixture model but with a mean parameterized by a Bezier curve. And what is a Bezier curve? A Bezier curve is essentially just a parametric curve that's parameterized by a handful of support points. And the cool thing about this is with this representation, you can actually fit this relatively quickly with the M. By relatively quickly, I mean only 21 days of compute time. And so what we do is we turn these 4.5 million trajectory segments into these clusters. Essentially, it's a clustering task. Here's what this looks like. Here, what you see here, all the little dots, the little, what we call these fishy plots, all these little dots are actual players moving. So for instance, one of these blue dots cutting from the left to the right along the baseline is James Harden when I'm cutting along. And the trail that it's leaving behind is the underlying parametric Bezier curve. Okay? So what you're seeing here is a handful of the actual segments, and then the sort of underlying, the sort of the cluster mean, you can think of that as. And so here's a bunch more. So basically, we took these 4.5 million segments, and we ran this clustering algorithm, and here are 8 more of the clusters. This is what they look like. So we actually don't have 8 of them, we have 250 of them. Okay, so we've taken all these segments, and we've clustered them using this Bezier curve idea, this functional clustering idea. And so where does that leave us? If you think about teammate interaction, we have this representation of a play as sort of evolving over time, and we slice up the individual player's actions. And now we've essentially colored those actions. So we've said, okay, in the beginning, there's one guy doing the purple action and 2 guys doing the red action, and then at some point player 3 switches to the blue action, and then player 1 switches to the green action, etc. So we've taken every player's movement, we've sliced it up, and now we've essentially assigned each of these segments labels. So we can say exactly what's happening over the course of a play. Now, we could just think about throwing each of those colors in and sort of thinking about the colors of the words. But it's just like when you're modeling text, if you think about modeling the word house and modeling the word white, that gives you very different outcome than if you model the bigram, which would be the word white house. Right? The words white and house tell you different things than the bigram white house. So similarly here, we want to think about pairs of actions. So our document is essentially throughout the play all pairs of concurrent actions. So basically every action pair that you've seen over the possession, we throw that in, that becomes our topic, or that becomes our document. And then we can actually skip over the details, but it's super vanilla latent heuristic allocation that there's probably like 10 R packages to do. What does this look like in the end? So again, we've taken all these plays movements, we've built this like document representation by labeling these segments, and now we're essentially fitting latent heuristic allocation. And what you get is every play gets a loading onto topics. And so what this is, these dots, every dot here represents a possession, and its location it's a higher dimensional topic space, but it's what you're seeing here is a lower dimensional representation. There are two plays which are close together in this space will be similar in terms of their topics. So again, every one of these dots is a basketball play, and we'll zoom in on two of them. We grabbed two of them that were the closest together in the data set, and here's what these look like. Anyone tell me what that is? What that is? It's the weave. It's the Warriors weave. And here's the other one. Warriors weave. Almost identical plays. So you'll also notice that, while I'm talking here, I'll play it again, that they both end the same way, within about 4 feet of each other. So what we've done here is, really we've just fed in the tracking data, and we've used all the actions that are happening by the defensive players, and then use those in a topic model, and then essentially it comes out to say, actually, these two documents are the two most similar documents in that data set, and you can see why. Here's the actual tracking data. When you actually watch the tracking data and you line it, you can see it really clearly why they're so similar. Stop. Here's another example. So what I've done now is I've taken every possession. I've actually done it to 2D now instead of 3D, because it's a little easier to see. And I've just looked at corner threes by possessions resulting in corner threes by 3 different teams. The Warriors, the Spurs, and the Rockets, colored by their relative teams. And the idea here is that you can take every corner three generated by these 3 teams, and you can then project it here and look at these different clusters and see how are they actually generating these corner threes. So let's zoom in on this right cluster. So there's a bunch of, so again, these are all plays. The closer in this space these dots are, these plays are, the more similar their semantic content is. So let's zoom in on one of these clusters and see what we see. All right, let's watch it. The truth is, I actually don't know what this set is called, but you'll see that it's the same thing. Now let me replay it quickly and show you what's going on. And then you'll see exactly why these come together. Look at the point guard, give the ball away, run down baseline. Screen hardens man, screen comes across. In this case, he doesn't get the shot. What's the same thing? Point guard, the post or the elbow, screens down, hardens man, and gets out for a shot. So it's interesting, right? Because in one play, I'll put it once more while I'm talking. In one play, Harden actually breaks, in the second one he breaks through and actually ends up taking the shot. In the other one he actually comes up short and someone else gets the shot. Okay. But the content of it's the same. It's still the giveaway, the point guard coming down, and the basket setting the screen on Harden's man while Harden makes a baseline cut. So it's kind of cool that if you actually looked at trying to use like play-by-play data, there's no way you would say that these could be the same, because the outcome was totally different. But when you watch the play, you realize they're almost identical. All right, so in conclusion, we have this way of in an unsupervised way, sort of creating this database of every NBA possession. It allows you to say, this possession is a weave, this possession is a hammer set, this possession maybe has some weave element, some hammer set element. You can do that automatically. That allows us now to answer some more contextual questions. Instead of just saying, okay, are the Warriors good? You can say, are the Warriors good when they run this type of play, or are the Warriors good when they run this type of play? And I'll stop there. Thanks.
So you said that these are grouped by how the sets are run, but the outcomes are very different. Is there any grouping that's done in reverse order, and more so looks at the outcome and then how that outcome is achieved?
Yeah, one thing you could do is you could like weight the end of the possession more. But we were really interested in saying a lot less about how the possession ended than about sort of what happened throughout the possession. Or you could like throw into the model, you could include like the ending state, for instance, as a word, right? And so then you'd get possessions which are more similar in terms of their outcomes. So you could absolutely sort of mess with this to weight it more towards the end of a possession or weight the outcome.
Yeah, so I think a big part of any kind of sports analytics in general involves being able to visualize the data well, and it looks like you've got incredible visualizations there. But I'm curious to know, even when you're laying it out like this, how is this received on the team end? And how does this come into play in terms of the analysis you conduct? Yeah,
mostly where it's received is by the team's like video people, because they look at this and they're spending so much time hand labeling a lot of things that are going on in the game, and they look at this and say, okay, this is awesome because you can look back now this season, you can do these things automatically. So it's more so, it's kind of a weird project in the sense that it's not something that you would like, if you show this to a coach, like, why would I care, right? It's more something that's like a pipeline, it's a tool.
If I understood you correctly, you're mapping the offensive sets and plays. Is there any mapping of the defensive players in terms of those two plays that were very similar, that had different outcomes? Clearly, a defensive player interacted there to prevent Harden from getting a three. Therefore, you can almost look at the same network from the defensive side of how to stop those plays.
Right.
This guy did this and then prevented that. Lower expected.
We have a model that tells you like who's guarding whom at every moment, and we looked at the offense-defensive pairs, and we were getting some interesting things. But you get a lot. It's a lot. You can definitely like include the defense, or you can somehow include using who's guarding whom to get like smarter words. But in the end, we got a lot like more interesting things to look at least in terms of when you just use the offense. Because the defense inherently is like responding to the offense, so it just sort of tends to add a lot of noise at least from what we saw.
One last question, guys.
Since there's always a little bit of variation in each play, like with that Rockets play, it was Harden shooting versus the other guy. How does the model kind of differentiate or know where the threshold is when it's either one individual action or one group of actions? Where's that cutoff point? How does it determine that?
So essentially, all that matters is that throughout the play, what concurrent actions were happening at the same time. And so when two possessions come close or very similar, it means that basically more or less means that the words contained in them are very similar. So it's not a threshold. It's what you end up with is every possession has, or every play I should say, has a loading onto all these topics. And so what will happen is that two plays will load slightly differently onto these topics. So one of them will be like, maybe it's like 90% weave, 10% hammer set, and the other one's like 89% weave and 11% hammer set. And so that's where you get the differentiation, is that because of that randomness, you load differently onto the topic distribution.
All right, thanks a lot, Luke. Give him another one.